Have you ever just stopped to look at a simple household item, something sitting right there in your kitchen drawer, and just marveled at the absolute dedication to a single, hyper-specific function? Well, today we're setting the stage for a really fascinating visual deconstruction into the functional design of everyday objects. In this explainer, we're going to take a seemingly invisible tool and break down exactly why it exists and, honestly, how it works so incredibly well.
So it all begins by asking a rather bold question. How can we engineer a faster snack? I mean, preparing fruit is something humans have done for literally millennia. It's a completely mundane, everyday task. But if there's one thing we know about human ingenuity, it's that we rarely ever settle for mundane. We're constantly seeking optimization. We want speed. We want convenience. We look at a piece of fruit and think, okay, how can I get this into my cereal bowl with the absolute minimum amount of physical effort?
Okay, let's dive into this. Look at this absolute marvel. This isn't just a basic piece of cutlery, right? This is the ultimate slicing gadget. It's a highly specialized, single-purpose tool born entirely out of the desire to conquer a simple banana. It's kind of fascinating why we invent tools like this. Instead of just relying on a multi-purpose chef's knife, one that can cut anything from a steak to a tomato, someone somewhere decided that slicing a banana required its very own dedicated piece of hardware. I think it perfectly captures our relentless drive to specialize.
All right, let's move to our first major breakdown. Section 1, Anatomy of the Tool.
Doing a bit of a forensic breakdown of these physical elements, we can see a brilliant contrast in materials. On the outside, we've got this soft, bright yellow plastic housing. It visually mimics the fruit it's destined to destroy, sure, but more importantly, it features an ergonomic tong-style grip. And this brilliantly illustrates how industrial design caters to human hands. The plastic is thick, it's rounded, it's approachable. But housed right within that safe, comfortable exterior are the business ends. Thin, rigid, unforgiving metal cutting blades. Basically, soft plastic for the human, hard metal for the fruit. And if you direct your attention really closely to those rigid metal inserts, you'll see a very specific number. 6. There are exactly 6 individual metal blades rigidly mounted in that plastic frame. They aren't random at all. They're spaced out with mathematical precision, designed to work in absolute unison. Just 6 distinct cutting edges suspended in space, waiting to be deployed.
Which perfectly transitions us right into Section 2, Mechanics of Motion.
Let's move to and see how this built. Shifting our focus to how this actually behaves in the real world, we've got a frozen-in-time look at a beautifully implied mechanical process here. It's a super simple 3-step action sequence. Step 1, which has already been done by our user, is to peel the fruit. Step 2 is to position those curved blades perpendicular to the length of the banana. And Step 3, this is the magic kinetic moment, is to squeeze the handle. We're capturing the exact millisecond before that final squeeze is executed. It's a totally flawless sequence.
We can actually define this specific action as simultaneous multi-blade deployment. Now, I know that sounds like something pulled directly out of a heavy machinery textbook, but right here in the kitchen, it perfectly describes the mechanism. This gadget transforms one single, relatively low-effort motion, a hand squeeze, into multiple, simultaneous cutting actions. It's just an incredible display of sophisticated engineering and ergonomic leverage, all packed into a $2 plastic gadget. You are literally doing the work of 6 knife chops with just one contraction of your hand.
And that brings us to the core purpose of this whole invention. Section 3, Efficiency and Uniformity.
Now, what's really interesting about this slide is exactly how those metal blades physically interact with the fruit itself. Notice the shape. The curvature of the metal is designed specifically and exclusively for the cylindrical, slightly bowed shape of a banana. They aren't your standard flat blades. They curve to intimately cradle the fruit's surface. And because of this tailored curvature, plus that fixed spacing we observed earlier, it ensures that when the squeeze happens, the output is exceptionally uniform. Every single slice is going to be the exact same thickness. So the crucial point is the sheer contrast in output. Think about traditional single-blade slicing with a standard kitchen knife. The math is super simple. One downward cut equals exactly 1 slice, right? To get 6 slices, you have to reset your hand and cut 6 separate times. But with multi-blade squeezing, one simple squeeze yields 6 slices instantly. Guys, that is a 600% increase in productivity per motion. It's the ultimate time-saving solution for an incredibly hyper-specific culinary task.
It really begs the rhetorical question, why slice once when you can slice 6 times? I mean, seriously, who has the precious time and energy to slice a banana piece by piece on a cutting board these days? The sheer efficiency of this device borders on the comedic for sure, but you absolutely have to respect the rigorous dedication to maximizing output from a single physical motion. It is over-engineered perfection.
It really makes you wonder about the environment around us. What other daily tasks could be totally revolutionized by hyper-specific, single-purpose design? As we wrap up today's explainer, I really want to challenge you. Take a closer look at the everyday objects around your own house. What unseen engineering is sitting right there in your kitchen drawers, quietly waiting to optimize your life one squeeze, one push, or one slice at a time? Look closely at the mundane, because honestly, design is everywhere. Thanks so much for learning with me today, and I'll catch you on the next explainer.